Here's a question most people never think to ask on a lighting project. What happens to your lighting system 6 months after the installation when the office layout changes? Because here's the thing, in most commercial builds, nobody asking a question during the design phase. They're focused on luminance, fixture counts, and code compliance, panel schedules, and that's all valid. But the moment that office decides to knock down the partition, expand the meeting room, or reconfigure the open floor plan, suddenly, the lighting system that was finished is now the construction problem again. So, here's a project background. A customer is renovating the office floor. You get open workstations, dedicated meeting rooms, shared collaboration spaces, a pretty standard modern layout, and the customer has a reasonable asks. Different lighting behavior for different zooms, occupancy-based response, scheduling, and ability to make changes later without a major rework. Sounds straightforward, but here's where it immediately gets complicated. In a traditional lighting system, your zooms are defined by your electrical circuits, panel, branch circuit. That's the hierarchy. And that works fine as long as the layout doesn't change. But the moment the layout does change, and in a modern office, you're looking at the circuit modifications, potentially new conduit runs, panel rebalancing, and what started, can we adjust the lighting zooms? The conversation has just become the electrical project. And that's the core tension here. The customer wants the flexibility. They want the control. They want the system to adapt as the space evolves. But the conventional path to delivering more control usually means more fixed wiring, more hard decisions locked in at the installation, and more cost every time something needs to change. Let me be clear, because I don't want this to come across as just dunking the conventional electrical work. Traditional AC lighting systems are proven, reliable, and absolutely the right call for lots of the applications. High voltage loads, industrial environments, projects where the layout is stable. The goal is straightforward, illumination. Conventional is still the right answer in those contexts. The issue isn't the traditional lighting is bad. The issue is that it's a poor fit for space that's designed to change. Fixed AC circuits are very good at one thing, delivering stable power to stable spaces. Well, they're not naturally built for frequent zooming, granular per fixture control, or lighting behavior. You want to update more like a software configuration than electrical modification. So when the customer says, I want to adjust the zooms without calling an electrician every time, that's not an unreasonable ask. That's just a requirement the traditional model handles poorly. Once you reframe it that way, the design conversation changes completely. The real question isn't how do we power these fixtures? The real question is, how do we build a lighting system that remains easy to control, easy to resume, easy to manage after space changes? That's control architecture question. And the answer looks very different from a traditional circuit layout. What this customer actually needs: zooming that can be redefined without touching the electrical infrastructure, scheduling that can be updated from management interface, so maintenance and troubleshooting don't require guesswork. When you list out like that, you're not describing a lighting specification anymore. You're describing a network device management problem. And that's where PoE lighting starts to make a lot of sense. For anyone who hasn't worked with a PoE in lighting context before, let's quickly establish what we're talking about, because the concept is easier to understand from the adjacent applications. PoE, Power over Ethernet, delivers both power and data over the single Ethernet cable. That model is already extremely well proven in IP cameras, wireless access points, VoIP phones, and access control readers. The reason it works so well in those applications is the same reason it's relevant here. It reduces dependency on local power infrastructure. Now, the obvious engineering question, when you start applying this to lighting is there enough power? And the answer is, for modern LED fixtures in office and commercial environment, is yes. Here's why that works. Modern LED technology is dramatically more efficient than lightning loads PoE was originally designed around. A well-designed LED fixture optimized for PoE delivery sits comfortably within what IEEE 2.3 BT. We're talking about up to 90 watts per port on the latest BT class switches, which opens up real headroom for commercial-grade fixtures with control electronics on board. So the power question is solvable. What the PoE actually changes isn't just how you power the fixture, it's entire infrastructure model underneath the lighting system. Here's the shift that matters most. In a traditional system, the lighting zone is defined by the electrical circuit. Change the zone, change the circuit. That's a physical. It's expensive, and it requires licensed electrical work. In a PoE-based architecture, the zone is defined in the software, in the switch management interface, in the control platform, in the VLAN policy layer. The physical cable runs to the fixture don't change. What it changes is how the system treats those endpoints. That's fundamentally a different model, and it changes the economics of reconfiguration significantly. A layout change that used to involve the panel schedule revision and can do the pull now looks a lot more like a network admin task. Scheduling updates, occupancy response, daylight harvesting, all of that integrates more naturally when the fixture is already a network-connected device. There's no separate control bus to wire up. The control path is a data path, which is already the cable you'll run to the power the light. Now, here's where we get into the real and actual engineering. And this is important because saying PoE lighting doesn't automatically mean the system performs well. There are two things that have to work correctly for this to be a real lighting system and not just an interesting network experiment. First, the backbone. You need a PoE switch that can handle aggregated power budget, provide a proper port management, and stay stable as a piece of a critical building infrastructure. Second, the fixture side. And this one matters even more than most people realize. LEDs are not generic DC loads. You can't just dump PoE voltage onto the LED arrays and expect a consistent, high-quality outputs. LEDs require a constant current drive. They need a regulation that accounts for thermal drift, forward voltage variation across the string, and a kind of the possession dimming control. It doesn't introduce a flicker or inconsistency across the fixture in the same zone. If that fixture-side conversion isn't done properly, you end up with a visible inconsistency between fixtures, degraded output over time, or both. And no amount of the smart network management fixes the problem that's happening at the LED junction. That's why, in this design, we started with a driver, not a switch. The driver we're using at the fixture side is Linovision PoE Driver 3.0, the 30 watts PoE input LED driver designed for professional lighting applications. Here's what the specs actually tell you from the electrical standpoint. Input: IEEE 2.3 AF80 compliant, supporting both Model A and Model B, meaning it works well with both 2 pairs and 4 pairs PoE delivery, which gives you compatibility across a wider range of the PoE infrastructure. The output: constant current 600 mA across 3 to 36 volt compliance range. That compliance range matters. 3 to 36 volts covers a wide range of the LED string configurations, series strings, shorter parallel service arrangement, and which gives you design flexibility at a fixture level without having to build around the single fixed output voltage. The constant current architecture is a critical part from a lighting quality standpoint. LEDs driven at constant current maintain more constant output across their operating range, respond more predictably to dimming control, and degrade more uniformly over time, which is what keeps the fixture-to-fixture consistency intact over the life of the installation. In short, this is a component that turns PoE from the power delivery mechanism into the proper LED drive system. Without something like this doing the fixture-side regulation, you're not really building a lighting system. You're just powering devices. Once the fixture side is handled, the backbone has to carry its weight too. And in this design, That's Linovision PoE SW708GM 8BT. Let's go through why this switch makes the sense for the lighting application specifically. Let's talk about the power budget first. 8 ports at 90 watts per port, IEEE 2.3 BT PoE++ with a 460 watts total PoE budget. For lightning deployments, that budget headroom matters. You want room for fixtures and any control or sensing devices sharing the same infrastructure without pushing the switching to the thermal throttling. At the management layer, VLAN, QoS, ACL, static routing, link aggregation, multiple remote access methods. For lightning, VLAN segmentation means you can isolate the lightning network from the general IT traffic, which is both a security best practice and reliability consideration. QoS gives you ability to prioritize control traffic, and remote access means change don't require a site visit. So let's put the full picture together, because the topology is actually pretty clean once you see it end to end. The unmanaged PoE switch lives in the IDF, the telecom room, or whatever network aggregation points make sense for the floor. From there, standard Cat6 Ethernet run out to each lightning point, just like the RAN network jobs, except these cables are also delivering up to 90 watts of the power. At each fixture, the PoE driver 30 picks up the cable, does a power conversion and constant current regulation, and it drives the LED load. The fixture is powered, controlled, and monitored over the same cable that delivered the PoE. Control, scheduling, zoning, and monitoring all happens on the network side. At the switch management layer or through whatever built-in automation platform set above it, zoning changes are the configuration update, not an electrical rework. Scheduling adjustments happen through the management interface. Occupancy sensors and daylight sensors can sit on the same network infrastructure, feeding data into the same control plane. The layout can change. The cable runs don't have to. If you're working on a project where the problem sounds familiar, this architecture is worth a serious look. Drop your questions in the comments, and if you want to go deeper on any specific part of this, driver selection, switch configuration, integration with a BMS platform, let me know and we'll cover it. And see you in the next video.